This section is about some elementary probability rules. This includes concepts such as the complements of events, unions, and intersections of events. This section also includes a discussion on the addition rule, which is used to compute for probabilities of unions. And we also have here conditional probability and independence. And finally, we have a discussion on the multiplication rule, which is used to compute for probabilities of intersections. So first, we have the concept of the complement. The complement refers to the set of outcomes wherein the outcomes are not part of a certain event. So we denote complements of events with the same letter as the event, but we add a bar on top of the letter or the word to signify that this is different from the original event, and precisely this is the complement of that event. So again, this just refers to the set of outcomes where event A will not occur. So that's A bar. That's the complement of event A. Now, complements are computed using this simple formula. So the probability of the complement of A, or the probability of A bar, is equal to 1 minus the probability of A. So if you add the probability of A and the probability of its complement, the sum will be 1 or 100%. So to compute for the complement, we use this formula. We have here a simple visual representation of event A and its complement. So the entire box here represents the collection of all outcomes, or the sample space, while the circle here represents the set of outcomes that are part of A. So all those that are not part of A, the one shaded in blue, represents uh, the concept known as the complement, and again that is denoted as A bar. Now we also have the concepts of unions and intersections, and these concepts are about the combination of two events. First, we have the intersection, so this is simpler compared to the union. The intersection of events A and B are elementary events that belong to both A and B. So this refers to the set of outcomes in the entire sample space that are both part of events A and event B. So here again, in the intersection, both events occur, or the outcomes part of the intersection are part of both events A and B, and this is how we write intersections. So that's A for the first event. We have inverse U to represent the intersection, and then B to represent the other event. So this refers to, again, the intersection of events A and B. The union of two events, on the other hand, refers to the set of outcomes that belong to either A or B or both. So this is composed of three parts. So it includes outcomes that are part of A only, exclusively A only. It also includes outcomes that are part of B only, so exclusively B. And finally, it includes outcomes that are part of both events A and B, or in other words, the intersection. So the intersection is a part of the union, and the union is also composed of the exclusively A and exclusively B outcomes. So this is written as AUB. So this refers to the union of events A and B. So in this slide, we can see visual representations of these concepts. Here in A, we can see the box representing the sample space and two circles representing two events. So the shaded part here represents the outcomes part of A. The shaded part here represents the outcomes part of B. The shaded part here represents the outcomes that are part of both A and B. And again, this is known as the intersection of events A and B. And finally, we have here the union of events A and B, which is composed again of three parts. Exclusively A, meaning the outcomes are part of A only. Then it also includes exclusively B, so outcomes that are part of B only. And finally, the intersection of events A and B. So combining these three gives us the union of events A and B. Now we also have this concept called mutual exclusivity, or events that are mutually exclusive. And events are said to be mutually exclusive if they have no sample space outcomes in common. Or in other words, these two events cannot intersect or do not intersect, or they don't happen at the same time. There is no outcome in the entire sample space that is part of both events A and B. Mathematically, this is how we write the presence of mutually exclusive events. So if the probability of the intersection of two events is equal to 0, again, it simply means that these two events cannot intersect, or they cannot happen at the same time, or in other words, they're mutually exclusive. So in this visual representation, again, the box represents the sample space. This is event A and this is event B. As you can see here, the two do not intersect. There is no outcome that is part of A and B at the same time, making these two events mutually exclusive. So an example can be the final grade in QMT 11 or in any subject. So let's say this refers to outcomes wherein the final grade is A, and this refers to outcomes where the final grade is B. We can see that they don't intersect because we can't have a final grade that is both an A and a B. So all the other events here outside A and B are all the other possible letter grades, such as B plus, C plus, C, D, and F. So all those are shown here outside A and B. But again, we can say here that events A and B are mutually exclusive because they don't intersect. Now, the addition rule is used to help us identify the probability of the union of two events. So if A and B are mutually exclusive, to get the probability of their union, just add their respective probabilities. So that's just probability of A plus the probability of B. However, if A and B are not mutually exclusive, meaning it's possible for A and B to intersect, then the probability of the union of A and B is equal to the sum of their individual probabilities minus the probability of their intersection. So again, here's if the two events are mutually exclusive, then the union is simply the sum of these two shaded areas. But if events can intersect, if we add P of A to P of B, we can see that a certain area is counted twice. That's why we deduct that once so that we can get only the probability of the union of A and B. Now, if the two events A and B are mutually exclusive, you can still use this formula. Because remember, if events are mutually exclusive, then it means that the probability of their intersection will be 0. Therefore, it will not affect the computation since the value that should be deducted is just equal to 0. So in this example, consider randomly selecting a card from a standard deck of 52 playing cards and define the following events. We have first J. This refers to the event wherein the randomly selected card is a jack. Q is the event where the randomly selected card is a queen, and R is the event where the randomly selected card is a red card, meaning the suit is either diamonds or hearts. So in that example, let's compute for the following probabilities. First, what is the probability that the randomly selected card is either a jack or a queen? So in this problem, it's asking not for one particular event only. It's also not asking for an intersection, and a clue here is the word or. Because of the word or, we can say that this probability is asking for the union of events J and Q. So to compute for that probability, for P of the union of J and Q, we will use the general formula, the addition rule. So that's the sum of their individual probabilities minus the probability of their intersection. And when you compute for this, first you need to get the value of P of J. Now, intuitively, we know that P of J is 4 over 52. But to explain how 4 over 52 is computed, we can use the general formula in computing for probabilities of events. Remember, J is an event, and to get the probability of event J, we have to get the sum of the probabilities of all the outcomes part of event J. And event J is composed of 4 outcomes. That's J of clubs, Jack of hearts, Jack of diamonds, and Jack of spades. Now, using classical method, we can assign the same probability to all these 52 outcomes. Therefore, the probability of each is 1 over 52. And we can use classical method here because we are randomly selecting one card out of the 52. So adding all these 4 probabilities will give us 4 over 52, and we will use that in the formula, in the computation for the union of J and Q. Now, using the same process for P of Q, we should get 4 over 52 as well. And then finally, we also need the probability of the intersection of J and Q. And here, we know that there is no card in the deck that is both a jack and a queen, meaning the probability of that is 0. Or in other words, we can say that events J and Q are mutually exclusive. Now, performing the operation, we will get a probability of 8 over 52 or 2 over 13. Now, for question number 2, it's asking for the probability that the card is either jack or red. So again, we have the word or, meaning it's asking for the union of events J and R. So to compute for this, we use the same formula. So that's P of J plus P of R minus the probability of their intersection. P of J again is 4 over 52. P of R, however, is 26 over 52 because there are 26 cards out of the 52 cards in a deck that are red, making this probability 26 over 52. And then finally, we subtract the intersection of the two events. So among all the 52 cards, there are only 2 outcomes that are both jack and red. That's Jack of hearts and Jack of diamonds, making the probability of this intersection 2 over 52. So performing this operation, we will get the final answer of 7 over 13. Finally, the probability that the randomly selected card is either a jack, a queen, or a red card represents the union of these 3 events. So that's the probability of the union of J, Q, and R. Now, the formulas that we have discussed so far only involve the union of 2 events. And in order to compute for the probability of the union of 3 events, we can start with the Venn diagram to help us in devising the formula. So here, again, the box represents the sample space of all 52 outcomes. We have here R representing the set of outcomes that are red. We have here J representing the cards that are part of event J. And we have here Q representing the cards that are part of event Q. So to compute for the union of the 3, again, we have to get exclusively all their parts and the intersections of the events. So one way to compute for this is to start first by getting the sum of all their individual probabilities. So that's P of J plus P of Q plus P of R. But whenever we do that, we can see that some areas are accounted for twice. Meaning we have to subtract this intersection, that's the intersection of J and R, and also the intersection of Q and R. That's why we have here the intersection of Q and R subtracted also to the entire function. So performing this operation, we have 4 over 52 for P of J, 4 over 52 also for P of Q, 26 over 52 for P of R. So get the sum of the three, and then subtract P of J intersecting with R, which is 2 over 52, and 2 over 52 as well for the intersection of Q and R, leaving us with the probability of 30 over 52, or 15 over 26.